Hello again. This is Math 1840, MFG version, coming to you from the College of DuPage. And this is problem suite 4 of 5. Please be an attentive learner, as always, when watching this video. So, problem suite 4 then, by way of introduction, there are men who knew infinity in the history of math. That is, in fact, the title of a popular and relatively recent film about Ramanujan. It was based on a book, The Man Who Knew Infinity. But way before that, in the history of math, it was an area of serious study, championed by someone who actually suffered greatly with criticism about these studies, George Cantor. And in addition to dealing with these, we will also talk about an unsolved number theory conjecture, which is a conjecture about the natural numbers, the first set of countable numbers. And these conjectures about natural numbers are a commonplace mathematical element, so it exposes you to this as well. So as you know from your reading, Cantor defined a set to be infinite if it is equivalent. That means there's a one-to-one correspondence, one-to-one and onto function to a proper subset of itself. Kind of a subtle definition, actually. If not, the set is finite. Moreover, Cantor defined a set to be countable if there is a one-to-one correspondence between it and the natural numbers. This was really countably infinite. And these are the numbers 1, 2, 3, ... So this first infinite countable cardinality, he called this alpha 0. And this is like a Greek letter. And so that is alpha 0. But then Cantor went on to prove that the rational numbers are countable. So there is a one-to-one correspondence between these numbers and the rational numbers. But the real numbers on the interval 0, 1 are not countable. In fact, this is a higher order of infinity, and he dubbed this alpha 1. And thus dawned a field of study called transfinite arithmetic. And we will not go any further in this, but I encourage you to read this as you get an opportunity. Okay, so there are, let's see, 1, 2, 3, 4, 5, 6, 7 parts to the first problem. So I'm asking you in parts A, B, C, and D to verify that the set of n sub e of all even natural numbers and the set n sub o of all odd natural numbers are countable. And I'm asking you to do the same thing for the sets z sub e and z sub o, which are all even and odd integers. Now recall that the integers are 0, plus or minus 1, plus or minus 2. So these are 0, plus or minus 2, plus or minus 4. And these are 0, plus or minus, actually 0 is even. So 0 is not odd, so this would be plus or minus 1, plus or minus 3, plus or minus 5, and so on. Now, this is 4 parts because this is part A, this is part B, this is part C, and this is part D. Now, part E is asking you to prove using a different formulation than the one that Cantor used. So prove by confirming that this function f, going from the rational numbers q, that's the m over n, where n and n are integers and n does not equal to 0, to the natural numbers defined by f of m over n is equal to 2 to the m times 3 to the n, that this is a one-to-one function. I.e., that means that the set q of positive rational numbers is countable because q is equivalent to f of q, which is contained within n. And finally, part F, verify this is function f going from the real numbers onto the 0, 1 interval defined by f of x is equal to 1/2 the whole of 1 plus x over 1 plus the absolute value of x, show that this is 1-to-1. And that shows you that the real numbers are in fact equivalent in a infinite cardinality sense to the interval 0, 1. Finally, part G, which is called the Collatz conjecture, which is about the natural numbers. And again, there was an article about Collatz that you read. So the statement of the problem is given here. What you're going to do is consider the following operation on an arbitrary positive integer, which is also what the natural numbers are. If the number is even, divide it by 2. If the number is odd, triple it and add 1. Sometimes people call this the 3x plus 1 problem or the 3n plus 1 problem. Now, if you were interested in this, really defines it all, but if you are interested in modular arithmetic notation, then this f would be defined this way: f of n is equal to n over 2. If n is congruent to 0 mod 2, that really means it's even. And if you have an odd number, you get 3n plus 1 if it's congruent to 1 mod 2, which means it is odd. So now what you do is you form a sequence by performing this operation repeatedly, beginning with any positive integer, any natural number, and taking the result of each step as the input into the next step. So in notation, a sub I is equal to n, if I is equal to 0, and I will give you an input there, but then it is f of a sub I minus 1 for I greater than 0, so you use this function. That is, a sub I is the value of f applied to n recursively I times. So a sub I is equal to f applied I times to the number n. These are called, of course, recursive relationships. Now, the Collatz conjecture is that this process will eventually reach the number 1, regardless of which positive integer natural number is chosen initially. Now, proving this is an unsolved mathematical problem, and so I am not asking you to do this. Recently, in 2019, there was a major effort coming close to the proof, and I can give you that reference if you're interested. But that's not what I'm asking you to do. I'm asking you to verify that the Collatz conjecture is true for n equal 3, 5, 7. I am asking you to show each step in the sequence in your answer. Okay, so that's that. And let's advance the slide then. So in closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important. And take care of each other, because we're all in this together. Strive to make a difference each day. God bless you all, and take care, and more soon.